Hello everyone, welcome to today's session on Analytics Deep Dive, Data Streaming, Querying and Sharing with AWS. Myself Kalyan Janaki, I'm a Senior Big Data Analytic Consultant, and today I'm joined by Uday Narayanan, Senior Solution Architect at AWS. As part of today's agenda, we will start our session by discussing about modern streaming data analytics architectures on top of AWS. Then Uday will talk about query federation with Athena and Redshift and other data sharing concepts of Redshift and Redshift ML features. Let's do a quick recap of key components that make up streaming analytics. The first component is of the source. As an example, it can be a clickstream data coming from mobile devices or web applications as a source. Then you have a streaming ingestion layer. So this is where you have an application tier that is constantly collecting the source data, such as clickstream data, and publishing it to the stream storage layer. Right. So the stream storage can be anything like services like Amazon Kinesis or Amazon MSK. And on the right side, you can see there is a stream processing. So once you have a stream data that's been collected, so you can process the stream data continuously for the sake of your real-time applications. And finally, the processed data can be stored into your destinations like data warehouses, data lakes for future analytics. Here is a simple architecture that brings all the components that we discussed in previous slide. With Amazon Kinesis data streams, you can build custom applications that process and analyze streaming data for special needs. Within seconds, the data will be available for your applications to read and process from the stream. What I would like to emphasize is the component consumption part of it on the right side. As you can see, we have so many number of options for consuming from Kinesis data streams. You have Amazon Kinesis Data Analytics. You can use Spark running on top of Elastic MapReduce, or you can use Kinesis Data Firehouse to read the data from your streaming data on top of your Kinesis data streams and load into multiple destinations. And you can build custom applications like consumer applications using Kinesis SDK and deploy them on top of Amazon EC2 instances, or you can use AWS Lambda for serverless consumption processing. Moving on to next streaming service in AWS streaming portfolio is Amazon Kinesis Data Analytics. Amazon Kinesis Data Analytics is the easiest way to transform and analyze streaming data in real time with Apache Flink. Apache Flink is an open source framework and engine for processing data streams. Kinesis Data Analytics reduces the complexity of building, managing, and integrating Apache Flink applications with other AWS services. It integrates with several AWS services and support custom connectors. Recently, Kinesis Data Analytics has launched KDA Studio. Kinesis Data Analytics Studio is a completely serverless and allows you to create stream processing applications very quickly. With few clicks, you can launch a serverless notebooks and query the data streams and get results in seconds. You can write code in the notebook in form of SQL, Python, or Scala to interact with the streaming data and get the response for your streaming queries within seconds. Once your code is ready for production, you can convert your notebook into an application and transition with a single click to a streaming application that can process GBs of data per second without having to manage any servers. The next service in the streaming portfolio that we'd like to talk is Amazon Managed Streaming for Apache Kafka. Amazon Managed Streaming for Apache Kafka is a AWS streaming data service that manages Apache Kafka infrastructure and operations, making it easy for developers and DevOps managers to run Apache Kafka applications and Apache Kafka connectors on AWS without having to need to become experts in operating Apache Kafka. So MSK Connect, Amazon MSK is a managed Kafka with a tight integration with many AWS services. You can use AWS Lambda to do a serverless consumer applications that can read data from MSK and do a real-time processing. You can use Amazon EC2 to launch your producer and consumer applications. You can use Amazon Kinesis Data Analytics and deploy the Flink applications to perform real-time streaming analytics on top of Amazon MSK. We also have a managed MSK Connect, where you can bring in your own connectors and run on top of MSK Connect infrastructure and interact streaming data with other third-party systems. So with that, having looked at the different streaming services in the streaming portfolio of AWS, let's review a few common streaming architectures patterns enabled by Kinesis family and MSK. So going into access log streamings. One of the standard streaming use case that we see many customers use access logs, streaming access logs. Basically, you can collect logs from any locations like web servers, application servers, and also so if you have logs from AWS applications like CloudFront or web application Fiverr logs that have been delivered to Amazon S3, you can get a put notification to an Amazon Q service, and you can have a Lambda subscribe to that notification and push all these log files into Amazon Kinesis Data Firehouse. Amazon Kinesis Data Firehouse is a streaming service in a Kinesis family which can load the streaming data into multiple destinations. It supports loading data into Amazon Redshift, Amazon OpenSearch, Amazon S3, and also it can deliver to custom HTTP endpoints, and it supports dynamic partitioning so that you can partition data in Hive style for effective data lakes. So in our use case, the logs messages or log events that are reaching to our Kinesis Data Firehouse can be loaded into your data lake for archival and future analytics. Or if you have a custom log security events that you want to do a reporting, you can load them into Amazon Redshift and have an enterprise data warehouses build the reports on top of it. Or if you want to perform some real-time windowed aggregations, you can have Kinesis Data Analytics consume that data and perform analytics. And finally, one of the biggest use case for log is a search solution. So users wants to have these logs into a search service like Amazon OpenSearch. So Kinesis Data Firehouse can load this data into Amazon OpenSearch, and you can use Kibana visualization for searching and visualizing your log files. Another architecture is for real-time reporting. So you might have many your SaaS applications or application databases, and you can implement any CDC solutions using Amazon DMS, or you can use an Kafka Connect running on top of MSK Connect and have this data streamed to Amazon MSK. So the source can be any applications like microservices or your application servers directly interacting with an Amazon MSK too. Once you have streaming data coming into Amazon MSK, you can have a Lambda processor that constantly consumes, modify the data, and send it over to your Kinesis Firehouse. And once you have data in Kinesis Firehouse completely manages of having these streaming data delivered to Amazon S3 data lake. Once the data is in the S3 data lake, you can do more ETL. So if you have a requirement to do transformations, you can make use of AWS Glue to transform the data and load it into your data warehouse running on top of Redshift and have a QuickSight reports run on top of it. Once all of this has been deployed, the data coming from your applications, front-end applications, can be sent over to your data warehouse in real time, and your reports running on QuickSight can be refreshed in real time. Moving over to next use case is near real-time search. We have many customers that use the DynamoDB because of its power and scale. So as an example use case, you can take an example of a real-time gaming application that's using DynamoDB as a backend. So you can stream the changes happening in your DynamoDB to Kinesis data streams and have a Kinesis Data Firehouse deliver it to an OpenSearch service, so that you can build an end-to-end real-time search solution, and the changes happening in your DynamoDB table can be automatically shipped in a real time to an OpenSearch service, and your users can use OpenSearch for searching these events. With that, we'll go ahead and take a look at the demo. Part of this demo, we'll be showing a sample clickstream application. We would be using MSK cluster to stream the clickstream data. And then we'll be using Kinesis Data Analytics application that process the data from cluster, aggregates, and then send back the aggregated data to the same MSK cluster for other topics, and also Amazon OpenSearch for search and visualization analytics. Moving over to an MSK console, this is an UI for Amazon MSK console, and let's see how you can create a cluster. When you click on the cluster, you have options for quick create and custom create. Let's take a look at quick create, custom create for more options. Then you'll have to provide the name of your cluster. Then you have two provisioning options. You have an option for serverless and provision. Let's take a look at the provisioned option here. As a first step would be used to select the Kafka version. I'll go ahead and select the default recommended version from MSK team. And then you have an option to provide the type of your broker node and number of zones you want your Kafka cluster to be deployed across, and number of brokers per each zone for larger distribution. And then you have an option to provide the initial storage that you want to assign for the broker nodes. You have an option to customize the configuration of your broker nodes, but in an example, I'll be using default MSK configuration. Moving over, because you have provided 3 AZs, you'll have to provide the networking details. I'll select and provide the details of my VPC here. So you'll have to provide 3 different subnets for 3 AZs. Okay, then you'll have to choose a security group for your MSK cluster so that your clients can access. So this is where you'll have to open the security group for your clients to have access and for produce and consume the data. Moving over to security settings, AWS Amazon MSK provides 3 authentication modes. It's IAM role-based authentication, SASL scram using password that is stored in your secrets manager, and also mutual TLS authentication with the TLS certificates managed by AWS Certificate Manager. And data is by default encrypted in transit between the broker nodes, and also you can have 2 modes between clients and brokers if you can have a TLS encryption enabled, and also you can, for your testing purposes, you can have a plain text encryption enabled. When it comes to monitoring, there are different levels of monitoring. We can have a basic monitoring, enhanced metrics at broker level, topic level, or individual partition levels. Then MSK supports the open monitoring with Prometheus, so that you can get this JMX exporter and have this JMX metrics sent over to your other application monitoring softwares or third-party softwares. Then you can select the logs, so you can have your broker logs delivered to CloudWatch, Amazon S3, or Kinesis Data Firehouse. In this case, we choose Kinesis CloudWatch. And then finally, you'll have to go ahead and click create on the cluster. But as cluster would take typically 15 minutes to create, I have a cluster that's already been running named as MSK cluster clickstream. So we'll be using this cluster. We'll go ahead and see a bunch of commands on this cluster. I have an EC2 instance with the Kafka client application installed on it. Let's go ahead and take a look at a list of all topics. So I have already created few topics in this Kafka. So example topic is our input topic, where we'll be streaming our clickstream data, and we'll have other topics for aggregation results of department level, click user ID level, and user session level. And moving over, let's go ahead and start producing the data. So I have a sample Java producer application that runs and produces the clickstream data to our MSK cluster. So this starts a Java application in the background and continuously streams sample clickstream data. So now that we have the data being streamed to MSK cluster, let's go ahead and see how we can deploy the Kinesis data analytics application. So this is the interface for Kinesis data analytics. I have already have an Flink application that's running. So if you click on the application, it's currently in the running state, and it has all the access to stream the data from MSK. And going into the configuration of application, you can take a look at the properties. So I have provided the details for Bootstrap servers and other topics and Elasticsearch endpoint for it to write the data to. So now that our Flink application is running, we can go ahead and take a look at the details of our data in Elasticsearch Kibana. So I have a Kibana endpoint running. So let's open it. So let's select the visualize section, and we have already a department count that has been enabled. You can click on the department count. As you can see, we have just started the streaming event, and that's where you can see the bump in the graph on the department count that has gone up all of a sudden. So you can always refresh it back and to take a look at last 4 hours, and you can see the data flowing for last 4 hours. I've been trying this POC here for last couple of hours here and there, and you can click on the refresh. That's end our today's demo on streaming analytics, and I would like to hand it over to Uday.
Thank you, Kalyan, and hello, everybody. My name is Uday Narayanan, and I'm a solutions architect at AWS. Today, I'll be covering 3 different topics with you. We'll do some presentations and also do a demo for each of those topics. We'll start off with query federation. So with query federation, you can facilitate on-demand access to data from multiple distributed sources in a single query. So traditionally, consolidating data from different disparate data sources required ETL processing to bring the data together into a shared format or to a central storage, such as a data warehouse. You would then run analytics on top of that data. With query federation, you reduce or even eliminate the need to do ETL because you're querying the data in place. Federated queries make it easier for data scientists and data analysts to analyze data using SQL, which is a widely used query language. And with query federation, it also becomes really simple to produce hybrid analytics and visualizations as well. AWS supports federated querying via 2 analytic services. The first one is Amazon Athena. For those who are not familiar, Amazon Athena is a serverless interactive query service that can process unstructured, semi-structured, and structured data sets. It uses Presto with full standard SQL support and works with a variety of data formats like CSV, JSON, ORC, Parquet, and Avro. Now, how does Athena do query federation? So Athena uses data source connectors that run on AWS Lambda to run federated queries. A data source connector is just a piece of code that can translate between your data source and Athena. Athena supports connectors to multiple AWS services as well as on-premise data stores, and it gives users the ability to run SQL queries on top of that data. With Athena federated query, you can run SQL queries across data stored in relational databases, non-relational databases, object stores, or even custom data sources. And as you can see on the screen, we have connectors to NoSQL services such as DynamoDB, Elasticache, DocumentDB, relational databases like RDS, Aurora, and Redshift. And we recently announced support for several new data connectors, including other cloud providers and ISVs. So some of the new connectors that we have are SAP HANA, Teradata, Snowflake, Oracle, and BigQuery. And these connectors are developed, open sourced, and fully supported by AWS. And there is no cost to using these connectors for you as a customer. And federated queries in Athena, enables many different use cases. We'll just quickly look at a couple of those use cases now. So the first is, you can combine and consolidate data from many different data sources and query it all in place. And as I said earlier, you can use familiar SQL to join data across multiple data sources for quick analysis and store the results in Amazon S3 for subsequent use. So think of a use case where you have like operational data in MySQL, you have some other data in a DynamoDB database, and then you have some other data, let's say, in Amazon Redshift, and you've been asked to consolidate all this data to do some analysis. So with federated queries in Athena, you can connect to all of these data sources, write a single SQL statement to join all of this data, and then the results of that can be written out to Amazon S3, which can be further used for machine learning or any kind of reporting analysis. You can also use query federation to do some light ETL work where you can connect these different data sources, bring them all together, and write out this data into Amazon S3, as I was just talking about. All right, so let's now go into the AWS console and check out a quick demo of how this works. So I'm going to go to Amazon Athena here. Yeah. All right. So before we start, let's talk about what we are going to see in this demo. Right. So here we are looking at orders data, which is currently loaded in an Amazon Aurora MySQL database. For those who are not familiar, Amazon Aurora is a global scale relational database service from AWS. It supports MySQL and or it comes in MySQL and Postgres compatibility. In this case, we are using an Aurora MySQL database. We also have a supplier table, which is also in the same Aurora MySQL database. And then we have a parts table, which is in Amazon DynamoDB. And we have a line items table, which is in Amazon EMR, and it's running on HBase. And then finally, we have a countries data, which is running on Elasticache on Redis. Right now, the business users come to us and say, hey, I want to know the total profit per country for each year. And in our case, because of the way the data is stored, it isn't easy because all of these data are stored in these different data stores. So this is where we can use federated queries to bring all of this data together and do the analysis. So the first step here is to create connectors that we talked about earlier, right? So as I mentioned earlier, Athena uses data source connectors that run on AWS Lambda to run federated queries. And a data source connector is just a piece of code that can translate between your data source and Athena. So there are two ways for you to create a data source connector, and I'll show you both the ways. The first one is to use the serverless application repository. So we'll create a DynamoDB connector now. So we'll go into the applications, and then we can search for DynamoDB like this. And then we'll pick the one which is the AWS verified version. So I'll click on that, and it brings me to this Amazon, the AWS Lambda page, where we need to provide it with some application settings. So I've already created this before the webinar, but I'll show you how to do it. So in this case, I'm just going to call it webinar. We need to give it a spill bucket. So as it's querying the data, if it needs to write it out like some temporary storage, it does that to Amazon S3. So this is my bucket name that I'm going to provide it. Then I need to provide it with catalog name, and this is the name that we will be using when we run the queries in Athena. Rest of it can stay default, and then we'll just give it the spill prefix. Again, this is the prefix in Amazon S3 where it is going to write the data. And then finally, I'll just say I acknowledge it, and we'll deploy. So now, what this is doing is it's actually creating a Lambda function, which will be used when we run Athena queries to federate with DynamoDB. It calls a Lambda function, and that's how the data comes to Athena. But as I said, I've already created a function beforehand. So if I just sort, I've already created one instead of Dynamo webinar. I just called it Dynamo. And in the interest of time, I'm going to keep going ahead with this demo. The second way to create a connector is directly from the Athena page or Athena console page. So when you come to Athena, you can go into data sources, and you can say create data source, and you see all of these data sources that we just saw in the presentation. You can select whichever one you want to federate with. In this case, as I mentioned, my data source is in MySQL, so I'm going to select MySQL. I'm going to click next. I'll give it a name, so we can name it MySQL over here, and you provide it with connection details, right? So if a Lambda function hasn't been created, you can just click on create Lambda function, and it brings you back to the same page that we just saw with DynamoDB. But in this case, I've already created the MySQL Lambda function beforehand. So I'm just going to click on that, and we can just click next and create data source. And our data source is available, or the data source connector is available. Right. So now once the connectors are created, running queries is as simple as running any normal Athena query that you would do. So in this case, let's just quickly run a query to connect to the MySQL database supplier table. So if I just go there and I say run. So at this time, it's actually using that Lambda function, and it is connecting to the MySQL database, and you see the results are here, right? We'll do one more. Let's just do DynamoDB, and I'm going to run it. And in this case, in DynamoDB, we are running a query on the parts table. And here the important thing to understand is it's a NoSQL database, but we are still running SQL queries on top of it using the Athena federated query. And again, so this is what our data in DynamoDB looks like. And just to confirm that this is the same table that we have in DynamoDB, I'll just go into the DynamoDB dashboard, explore items, part, and you will see that you have a part key, brand, comment, container. And if I come back here, you have a part key, brand, comment, container, right? So it's the same table. So you're running SQL from Athena into the DynamoDB table. Now, going back to the use case where our business wanted to get the total profit per country for each year, I have this query here. So as you can see, if you look at this particular subquery, we are querying from the DynamoDB table or the DynamoDB part table. Then we have the supplier table coming from MySQL. We have the line item table coming from HBase, which is running on Amazon EMR. We have the parts table coming from DynamoDB as well. We have the orders table coming from MySQL. And then we have the nations table coming from Redshift, coming from Redis. And then we have these where clause that's kind of joining all of this data together. And then in the select statement, we're just getting the nation information, the year, and then doing some calculation to calculate the sum, the total amounts. And then outside the subquery, we are just summing the amount to get the total profit. So if I just run this query, as you can see, right, instead of bringing all of this data together into a central storage, we are just able to run one query within Athena, and using federated queries, we are able to access the data in those different data stores. And we get our results back. So, we get it by country, by year, and the total sum of profit. All right, so that's the Athena federated query demo. We'll go back to the presentation for the next topic, which is federated queries using Amazon Redshift. So Amazon Redshift is a cloud data warehouse provided by AWS. And by using federated queries with Amazon Redshift, you can query and analyze data across operational databases, data warehouses, and data lakes. And again, the idea of federated query is the same in Redshift, like we talked about in Athena, right? It's querying data in place from these different data stores. So this capability enables a new data warehouse pattern, which is live data query, in which you can seamlessly retrieve data from PostgreSQL or MySQL databases, or build data into a lake binding view, which combines operational data, local data stored on Amazon Redshift, and historical data in Amazon S3. Now, if you look at this diagram here, I don't want to go into too much detail into how this Redshift architecture works, but you have a client on the top, and you're connecting to a Redshift cluster. When you're connecting to a Redshift cluster, you're connecting to the leader node. Leader node is the one that does all of the coordinating. And then you have compute nodes, and you can have any number of compute nodes depending on the size of your cluster. And compute node is where all of the work for running the query is happening. The results are sent back to the leader node, who then sends it back to the client. right? So now when running federated queries, Redshift first makes a client connection to the RDS or Aurora database instance from the leader node to retrieve the table metadata. From a compute node, Amazon Redshift issues subqueries with predicate pushdown and retrieves the result rows, or retrieves the data back. Amazon Redshift then distributes the result rows among the different compute nodes for further processing. And once the processing is done, the result is sent back to the client. So with Redshift Query Federation, you can integrate the data on your Amazon Redshift cluster with operational data in RDS or Aurora MySQL or Postgres to perform powerful analytics. So as discussed, with this feature, you can perform analytics on your operational data without having to move the data into your data warehouse in Redshift or running into any kind of delays with complex ETL processing and ETL tasks. You're running these queries directly on your data source and hence have access to the most up-to-date data. And once you are able to access the operational data stores, you can bring the data from multiple data stores and your data warehouse and your data lake all together by joining them and building reports, which can then be used for doing any kind of ML analysis or downstream analysis, business intelligence reports, and so on. And again, the important point here is that all of this is being done by querying data in place without having to move data from one place to the other with ETL. All right, so now let's go back to the console and just take a look at how Redshift Query Federation works. Right, so for this particular case, I have, I'm going to go here and actually open the RDS console, and we'll take a look at the database that we have created for this. Right, so if I go into my databases, I have this database lab database that I've created. It's a serverless database, and it is a Postgres, Aurora Postgres. Right, so if I just do a go into my query editor and I quickly connect to it, and need to get my and I'll talk about what the secrets manager is doing in this whole thing. But for now, I'm just going to use this to connect, and my database name is Postgres. Right. So as of right now, I have this serverless database, and I have one table, which is a customer table. So if I just go and just do a quick query on this customer table, you will see it currently has 4 rows in it. Right, so this is my data that looks like. Now I'm going to keep the demo for the Redshift Federation very simple. All we're going to do is we're going to go to a Redshift cluster and try to access this data from there. So how do we do that? So let's go into my Redshift cluster here, and I'm going to use this marketing cluster for this. And I'm just going to reconnect. And the first step is you create an external schema. So in this case, I'm going to name this external schema as Postgres. We need to provide information of where is this schema coming from, like what kind of schema it is, or what is the source for this particular schema. And in this case, it is a Postgres database. And in this case, the database name is also Postgres. Now, this URI is the connection information for your database, right? So if I go back into my RDS console, and if I go into my databases, and I click on this database lab, you will see that it has this endpoint, which is database lab cluster and a whole bunch of information, and then Amazon.com. And that is the same thing here, database lab cluster, a whole bunch of information, and then Amazon.com. You then need to provide it with an IAM role. This IAM role is giving Redshift permission to access the RDS database. And then finally, you have the secret ARN. And this is where all of my username and password and all of that information is stored. Right. So if I go into my secrets manager, you will see that I have this secret created. This is the secret ARN, which is what we have on the Redshift query as well. And then if I look at the secrets that's there, it'll show that the username is Postgres, the password is this value, it's a Postgres engine, this is the host, the port, and the database identifier, which is the database lab, which is the exact same value as what we have here. Okay. And again, if you look at the secrets ARN, this is the same value that we are going to provide over here. All right, so enough talk. Let's just run this query. Now, okay, so now the external schema is created, and Redshift is now able to connect to our Postgres database. So if I just run this query on the customer table, you see those same exact 4 rows that were there in RDS. They show up here as well. So now, just to do another quick test, I'm going to go back into my RDS console, into my query editor, and I'm going to run an insert statement just to insert a new row, and it succeeded. Now, if I come back to my Redshift cluster and do a select star for that table, the 5th row also shows up. So as you can see, right, with this, you don't have to worry about doing any kind of an ETL to move the data from your relational data stores into Redshift. As data is inserted and updated or deleted in your operational store, you have immediate access to that data here. All right, so now let's go back to our presentation and on to our next topic, which in this case is Redshift data sharing. Now, data sharing provides live access to data so that your users are always seeing the most up-to-date and consistent information as it's updated in your data warehouse. You can securely share live data with Amazon Redshift clusters in the same or different AWS accounts, as well as across different AWS regions. But before talking about Redshift data sharing, let's look at how customers used to share data between clusters before this feature was available and the challenges they faced. Many customers who use Redshift have multi-cluster deployments. In order to share data between clusters, customers have to manually unload the data and copy the data from one cluster to the other. The producer cluster is where the data is getting copied from, and consumer cluster is where the data gets copied to. Now, on the producer side, this process to manually unload and copy the data can become cumbersome and expensive. And it usually becomes cumbersome when the number of clusters in the organization grows. You also need to incorporate security and governance into this to make sure the consumers are only getting access to the data they need and nothing more. There are challenges on the consumer side as well, because you need to reconstruct the data that is coming from the producer cluster. You need to manage the schema changes. There are also challenges on the there are also challenges with the stale data, because the ETL job that is not running continuously, right? So whenever the ETL job runs, the data is accurate. Until it runs the next time, the data starts becoming stale, which means you cannot really provide real-time insights to the business. And then there's also concerns around incomplete and inconsistent views of the data, and then you're creating data silos. All of this results in business losing trust in your data because of inconsistent results. This is where Redshift data sharing comes in and helps solve these challenges. So data sharing was launched as a simple and secure way to share live data across multiple Redshift clusters. So this allows customers to access live data in a transactionally consistent fashion without having to deal with ETL processing or data copies. The owner of the producer cluster has the flexibility to share the data at either a database level, schema level, table level, view, or a SQL user-defined function level. The consumer cluster gets immediate access to the data. There are no delays. This means as and when there is an update in the producer cluster, the consumer cluster is getting immediate access to the data, and the data is transactionally consistent. So when a query is run on the consumer cluster, you will see the latest data. Data sharing also provides secure and governed collaboration. you can share data within your organization or with your external customers or partners. The producer cluster will always maintain control of the data set. At any point, if access is revoked for the consumer cluster, that consumer immediately loses access to the data. And as I said earlier, with Redshift data sharing, you can share data between Redshift clusters within the same AWS account, across multiple AWS accounts, and across multiple AWS regions as well. Now let's just quickly talk about how this works, right? So with Redshift data sharing, or Redshift data sharing is built on Amazon Redshift RA3 nodes and Redshift managed storage. With these RA3 node types, you can scale your storage and compute independently of each other. As you can see in this picture, we have a producer cluster on the left, which is sharing some objects with the consumer cluster on the right. The data is stored in the Redshift managed storage layer. When the consumer cluster is running, when the consumer cluster is running the queries on the shared object, the compute from the consumer cluster is being used, but the whole data access is happening through the managed storage layer. So there is no impact to the producer cluster here. The producer cluster and the consumer clusters are just regular Redshift clusters. So, the consumer cluster has read-only access to the objects shared by the producer cluster. But at the same time, the consumer cluster can have its own private data that it can read and write to. From a cost perspective, the producer pays for managed storage and the consumer pays for the consumer cluster. Data sharing does not come with any cost associated with it. Now, there are different use cases for data sharing. I'll talk about one such use case. And this is around workload isolation, where you need to support diverse business critical workloads easily and cost effectively while still maintaining the SLA requirements. So with data sharing, you can rapidly onboard new analytics workloads. Now think of a scenario where a developer reaches out to a data warehouse administrator saying they need to do some analysis for the sales data in the production Redshift cluster. The administrator does not want to give the developer access to production. So the administrator can tell the developer to spin up their own Redshift cluster in a dev environment and then share the data they need with the developer cluster. This way, the developer gets read-only access to the data within minutes of requesting it. The consumer does not need to worry about where the data is coming from and do any kind of ETL. With this approach, we are also preventing the creation of data silos. The second aspect of workload isolation is you can size and scale individual workloads according to the performance requirements. So as you can see in the picture, we have an ETL cluster, a dashboard cluster, and a data science cluster. Depending on the performance needs, all of these clusters can be sized differently and can have different node types and number of nodes as well. And finally, you can pause and resume clusters as needed. So let's say the ad hoc query cluster is only being used for a few hours in a day. You can pause the cluster during the times it's not being used to save costs. All right, so now let's again go back to the console and check out the data sharing capability in practice. All right, so now here we'll be using two different clusters. So I have this Redshift producer cluster, which is in the Oregon region. And I have the same marketing cluster that we had used in the past, which is in the North Virginia region. So what I'm going to do is I'm going to share some data from the producer cluster, and my marketing cluster is going to be the consumer of the data, right? So now in this case, if I look at this Redshift cluster in the public schema, it has 9 tables, but as a producer, we want to share some data with the marketing team, but we don't want to share all the tables with them, right? So what we decided was, okay, we can create a view based on the information that the marketing team needs, and share the view with them, right? So I'll just create this orders marketing view. And if I just do a quick query for that, we'll check out what the data looks like. Right, so it has all of this information that needs to be shared with the marketing team. Now, the first step to create, for data sharing, the first step that we need to do is to create a data share. So in this case, we'll create a data share and call it the marketing share. And a data share is just a unit of sharing data in Amazon Redshift. Now, once the data share is created, we add objects to the data share. So in this case, we're going to add the public schema. This is where the view is created. And then we'll add the orders marketing view that we just created, right? So these two objects have been added to our data share. Now we can just quickly take a look to see what our data share looks like. Right? So if I run that, you'll see a marketing share has been created. And it is an outbound data share, which means this cluster is the producer, and it is being shared with some other cluster that would be the consumer of this. That's what outbound means here. We can also check what objects are being shared by this data share, and we'll see the same schema and view that we just added. And let's check out what consumers we have. And we don't have any consumers because we have not added any consumers yet. Now, in order to add consumers, to this data share, you run this command, which is grant usage. So you run grant usage on data share, marketing share, which is the data share we created. And then we give it a namespace, like which cluster are we going to share this data with. Now, this namespace comes from the Redshift console. So if I go back into my Redshift console, this is my marketing cluster. That is my consumer. And then there is this cluster namespace right here, right? It starts with phi9 and it ends with B1. And that's what we see here. It starts with phi9, it ends with B1. So this is telling Redshift that, okay, I created this data share and I want to share this data share with the marketing cluster. Okay, so this takes care of the producer side of things. So this is all you need to do on the producer side. Now, if we go to the consumer side, and I go into this tab here. First, we'll just quickly check to see what data shares are available. So in this case, the marketing share is available, and it is an inbound data share, which means in this case, the marketing cluster is the consumer. The next step is to create a database, which is a local database to the shared objects, right? So again, here we are. Oops, I'm just going to do that. So in this case, we're going to run this query to create a database called consumer marketing from the data share, marketing share, which was shared with us, of namespace this, and this is the cluster namespace for the producer cluster. Next, we need to grant usage on this data share to AWS, to the users who are using this Redshift cluster. And that's pretty much it. Now, the data is available for us to run queries here, right? And again, the important point to understand here is that this particular view was shared with this marketing cluster from the other cluster, the other producer cluster, right? So the other producer cluster still manages the data. They have the ability to revoke access. Marketing cluster is just getting access to the data because it was shared with this particular cluster. Okay, now let's actually go and check to see what happens if the producer cluster revokes the access. So I'm going to switch my tabs. I'm in my Oregon region, and this is my producer cluster. And I'm going to say, okay, I don't want marketing cluster to have access to this data anymore, so I'm going to revoke the access. All right, now let's switch back to our marketing cluster, who is a consumer, and then rerun this query that just worked like a minute back, right? And now I get an error saying that the cross-region data share does not exist. And why is that? Because if I come to the data shares, I don't see any data share anymore because the access was just revoked. If I go back to my producer cluster and I again grant access, And then I switch back to my marketing cluster, that is my consumer, and I rerun this query. I see the marketing share again. I see the inbound share type. And when I rerun this query, everything should just work as it was working before. All right, so that brings me to the end of my data sharing demo. I just have one last topic. So we'll go back to the presentation and we'll talk about Amazon Redshift ML. So Amazon Redshift ML makes it easy for data analysts and database developers to create, train, and apply machine learning models using familiar SQL commands in Amazon Redshift. So with Redshift ML, you can take advantage of Amazon SageMaker, which is a fully managed machine learning service, without learning new tools or languages. And just using simple SQL statements, you can create and train Amazon SageMaker machine learning models, and then you can use those models in your Amazon Redshift data warehouse. And again, you can access them by running simple SQL statements. So because Redshift ML allows you to use standard SQL, it is easy for you to be productive with new use cases for your analytics data. And to get started, all you need to do is run a create model command, which and when you run the create model command, Redshift is integrating with Amazon SageMaker, and it's creating the models for you. And once the models are created, you can use those models in your select statements. And if you already have models created, machine learning models that have already been created, Redshift ML also supports bring your own models. So you can bring your own models in here as well. Right. So just a quick overview of how this works. So when you're creating the model or when you're training your model, you're just running the create model command, and you provide it with either a table name or a SQL statement. And then you provide it with the target column. So in this case, I'm trying to do a churn analysis of how many customers are leaving a certain company. So the label column is where that data is stored. So it'll either have a value of true or false. So you need to provide it with the target column. And finally, you give it a function name, which in this case, I call it predict_customer_churn. When you run this command, Redshift is integrating with Amazon SageMaker Autopilot. Autopilot is like going through different models, doing some hyperparameter tuning, and it comes up with the best model for this particular data. Now, once the model is created, you can use that model in your SQL statements. And you do that by running predict statement, you run that to predict the data or to do some predictions on the model. You just use the function called predict_customer_churn, which is the same function name that we provided in the train section. And then you just provide it with the fields or the columns that go as an input to that function. When you run the SQL statement, you get the results back, right? So as you can see, two simple SQL statements, and you have a machine learning model that you can use in your analysis. So there are different use cases, but some of the common use cases are to do churn prediction. That is what we just talked about. If you want to understand the engagement rates for a certain campaign that you're running, fraud detection, revenue prediction, customer behaviors of how customers are behaving based on certain campaigns, all of that can be done using Amazon Redshift ML. And again, this is just a small subset of use cases. There are very many different use cases out there for this particular feature. All right, so my last demo for today, I'm just going to go back into my console here and we will go and do a demo for Amazon Redshift. So in this case, I have claims data that I have already created. Claims data table, which I have already created. And this is what my data looks like. But the important part here is there is a fraud column in this data set, right? And I want to identify the fraud column for future data that is coming in. So the first step in any machine learning use case is you split your data into training sets and test data sets. So here I'm going to run this query to create a training data set. So for any, the first 7,500 rows go into the training data set, and the rest of the data goes into my test data set, right? So I just created two different tables for this. Now, as we talked about it earlier, I'm going to run this statement, which is going to create the model. So I'll just run it. So here it is creating this particular model based on this particular SQL statement. And again, it is querying the training table. My target column is fraud because I want to identify the fraud. And this is my function name. And then you provide it with an IAM role and S3 bucket where all the model artifacts are stored, right? So if I just quickly run this show model command, you will see that the model is currently in training. This training can go on for like an hour or a couple of hours depending on your data set, which is why I have already run this once before. And if I do a show model for that, you will see my model state for this one is ready. It's the exact same model. I followed the exact same steps, right? Now, once the model is created, you can run inferences on top of that data, right? So here I'm just running, getting some information from my table. And then I'm using this function insurance fraud model, which was the function name that I provided when I created the model. I provide it with these 3 columns, and I wanted to calculate the fraud. And again, I'm doing this on the test data set. So the machine learning model was not run on this data set. So this is brand new information for us, right? And it's doing this, it hits the model, it, based on the model, it determines, okay, for this particular user, this transaction is not a fraud, but for this one, this transaction could potentially be a fraud. Right. So as you saw, just writing a couple of simple SQL statements, you're able to build powerful machine learning models here in Amazon Redshift using the Redshift ML feature. All right. So that brings me to the end of the presentation today. We covered a lot of different topics. So we have sharing some additional resources that you can use to, check out the topics that we talked about and go in a little bit more detail. So this page provides the features or additional resources for the query federation feature for Athena and Redshift. And then we also have some additional features, additional resources for the data sharing and Redshift ML features that we just talked about as well. All right. So with that, I'd like to thank you all for attending. Have a great day, everybody. Thank you.